Greetings students, welcome to this short video on experimental design, and I want you to note that we are saying experimental design continued because a couple of work has already been covered by my colleagues. So in this short tutorial we shall be looking at factorial design. This is a continuation from the previous work that you have covered already. For the avoidance of doubt, allow me to highlight you have already been introduced to experimental design, and in particular you have covered the three types of designs. That is the CRD, that is the complete randomized design, the randomized complete block design, and last week you were introduced to Latin square design. What I want you to appreciate from the onset is the fact that each design is suitable for a particular circumstance. You don't just choose a design for the sake of it, but you choose a design to use in a particular experiment, being guided by the nature of the experiment vis-a-vis what the design is able to capture. Obviously, I know you were introduced and explanations were given extensively that for you to use a CRD, you must assume or you must be convinced that the environment is homogeneous. So it must be used under controlled environments, either in a laboratory or in a greenhouse, where we don't expect intruders or some extraneous variables to come into play. And now, moving on from that, you were introduced to randomized complete block design, where the environment now is heterogeneous, but there is only one factor which can intrude into your experiment. Now, last week you were introduced to a Latin square design, where it was explained to you that now, in the event that there are two factors that needs to be blocked, if you want to block two factors, you must use a Latin square. Why am I narrating this? I'm narrating this simply because today I shall be talking of factorial design. So in the same line, I want you to appreciate that use a factorial design because of the situation that confronts us as researchers, as you shall see as we proceed. Now, what is a factorial experiment? So when we talk of a factorial experiment, it is a study, the study of the effect of two or more factors. Two or more factors. The moment we talk of two or more factors, we have factorial. In fact, the name factorial comes from the issue of having a number of factors. So in each complete trial or replicate, I'm sure you were taught the three principles of experimental design. So when we talk of replicate, it's not a new term to you. We are simply referring to a repetition. So in each complete trial or replicate of the experiment, all possible combinations of the levels of the factors are studied, right? Now, why not one factor at a time? Why not studying one factor at a time and then we move on to study another factor? Obviously, it is logical, and I'm sure all of you would appreciate that studying one factor at a time is time consuming, because it means you have to run the experiment completely up to the end before you introduce another factor, and then you come introduce another factor. So you see, when you do one factor at a time, it is as good as you are given a task, say for instance, to transport people from, say, Hendy's Bay to Vindu, and those people are 4. So instead of driving all of them, you put one person, you drive from Hendy's Bay up to Vindu, then you go back, you go take another person, you drive until all the 4. So instead of doing that, you would rather put all the 4 people for as long as they can be accommodated. You drive all of them at once. So we don't use one factor at a time because we want to save in terms of time. So that is the instance of factorial. And from the example that I've already given you on transporting people, obviously, if you do one factor at a time, it becomes costly. It becomes costly because you will have to lay down a number of separate experiments, which obviously have got time. You know, time is money. You lose on time. And also, of course, you may need fixed costs will still remain when you run an experiment. Fixed cost, if it is watering, instead of just watering once and all the factors are benefiting from the watering process, you will have to water for this factor and then you water again. Now it is less efficient. We are going to, as we proceed with the video, I want you to why I'm saying it is less efficient. In fact, there is a lot of evidence that points to that, as we are going to discuss. So, in short, I am simply saying, if you are investigating more than 2 factors, not more than 2 and above, in fact, you can have actually 2 factors, we are already talking of a factorial experiment. We are already talking of a factorial experiment. But if you are just investigating 1 factor, then that is not a factorial, because the factorial, we are simply saying 2 factors and above. And now the reason why 2 factors and above is because of these issues that I've highlighted to you here. Now, we are still continuing. Why factorial? Consider the introduction of a new plant variety in a country. Ladies and gentlemen, I want you to understand that as it stands now in the country, in Namibia, we don't have locally produced maize varieties. A lot of work is underway now to try and do some breeding programs locally so that we have varieties that are produced within the country. So if we are to develop any new variety, it's not only of maize, any plant, before it is released, a number of information is needed, because when you release a variety, the farmers would want to know what is the spacing for this variety, what is the fertilizer requirement, how tolerant is it to drought, do we need to irrigate or not, what is the timing. Now, if you look at this, all these factors, these are factors. So if we are to introduce a new variety and we want to avoid factorial, what it simply means is that you need to investigate spacing. So you may have different spacing dimensions. You know, spacing is defined by in-row and inter-row. So you may have to define maybe a couple of spacing dimensions. You lay down an experiment. maybe for 2020, you are investigating the spacing requirement for that particular variety, then you get your results. And mind you, for most of the agronomic experiments require data, almost a minimum of 2-year data. So for spacing, you do need 2 years for the experiment to be conclusive. Now, you move on to fertilizer requirement. Maybe for fertilizer requirement, it can be an exception. You may just do a single trial in a year. Now you move on to irrigation, where you may want to test the drought tolerance of the new variety. And then you do timing, where maybe you may say you are planting, early planting, maybe November, December, January, and so forth. Now, if you do it that way, this variety will not be released at all. It will take a couple of years. In fact, the researcher might even die before getting the results or communicating the results. So I want you to see how handy factorial experiments now become. Because what is happening, instead of investigating each of these separately, we can actually put a single experiment. Of course, we should not add too many factors, because the more the factors, also there will be a compromise in terms of quality, in terms of efficiency. So we may have 2-3 factors that are included in a single experiment. Instead of taking 3 years, we may shrink that to a single year and investigate all the factors. Now, this is what I'm saying here. If we do not go factorial, it means several experiments that may take years before understanding the agronomic requirements of the plant. Obviously, that's not what we want as researchers. We want results as soon as possible so that we are able to move forward. I have given you another example here to try and make you understand why we go factorial. Suppose we are developing new feed formulations. How much is needed when it comes to feeding? Maybe this is animals, we are feeding animals. How much do we need to feed the animals? Which breed will have more weight gain? In fact, is the feed formulation resulting in more weight gain compared to a particular other feed which might be present? Do we need to do any feed restriction and so forth? In that case, we may need to have a factorial arrangement where we just test all the factors at once. Investigate the issue of restrictions, investigate the issue of how much is needed, and so forth, and then we communicate the results in a single run. Now, I want you to note that at this point, a single factor experiment is the simplest form of carrying out research, but will not explain a biological system where there are many interacting factors. And I want you to see the terms that I'm highlighting for you. They are very key terms, and you do need to have a thorough understanding. So if you do a single factor experiment, it is simple, but simplicity is a compromise in terms of inability to explain a biological system where there are many interacting factors. Okay, we are still continuing with why factorial. An organism's response to a single factor may vary with the level of the other factor. I want you to appreciate. I will give you a simple example here. If we are investigating, for example, milk production for cows, and perhaps we strongly believe that the milk produced or yield of milk is dependent on the type of feed that we have given to the animal. We may not ignore the issue of temperature. We may not ignore the issue of temperature on that particular day in question where the milking is taking place. So you would realize therefore that the response, in this case we are talking of milk yield as the response. Milk yield to a single factor, which is the feed that we have given the animal, will also depend on the temperature. What temperature is it? Temperature is a factor. The different levels within a temperature is what we refer to as treatments. So treatments are the levels within a factor. Temperature is a factor. When we say 30 degrees, 40 degrees, 50, those are the treatments. They are the levels within the factor. Now, single factors are criticized for narrowness. When we say something is narrow, it means it fails to capture broadly issues that are very much closer or in the vicinity of that particular thing. So a single factor experiment is only applicable to a particular level in which the other factors were maintained during the trial. So if we just investigate milk yield as a function of the feed that we have given in that particular day, what it simply means is that we cannot vary temperature and still expect the results to be applicable. So that is why we are saying a single factor is narrow, because whatever results you are getting pertaining a particular factor is only applicable to the level in which the other factors were kept constant. Once the other factors change, we don't expect the same results to be applicable. So if the milking was done when the environmental temperature was 40 degrees, now if the temperature goes up to 48, we don't expect the same milk yield even whilst giving the same feed which was tested previously. So that is the narrowness part that we are talking about. So I put a question here. This is food for thought as you are going through this video. Is it then practically applicable if we are doing biological experiments and we are just testing one factor? Is it biologically applicable? Is it then practically applicable? How practical is it? Obviously, one would want to say, yes, it's practical. But I want you to consider situations. Yes, it can be practical in some situations where we totally assume that the factor which is being investigated is the only factor that can influence whatever we are measuring as the response. But in the event, in most cases actually, we don't always have a single factor being a determinant of the response. We might have quite a number of factors interacting, in which case then, if we do a single factor experiment, we may suffer the danger of narrowness. Now, allow me at this point to explain factorial. In statistics, a full factorial experiment is an experiment whose design consists of two, I said two, from two and above, or more factors. Yes, two or more factors. Each with discrete possible values or levels. When we talk of discrete, countable, 1, 2, 3, 4, 5, and so forth, that is discrete, not 1, 1.5, I think we did this in biostatistics. So discrete possible values or levels. So we are talking of the factors. The factors are the ones with discrete levels, discrete possible values or levels, and whose experimental units take on all the possible combinations of these levels across all such factors. A full factorial design may also be called full crossed design. It simply means the same. But one might ask, why is it called crossed? We are crossing the factors. When we are forming combinations, it's like we are crossing the factors. Of course, this is my explanation. This is what I think when we look at the term crossed. Such an experiment allows studying the effect of each factor on the response variable, as well as effects of interactions between factors on the response variable. This is the greatest advantage of factorial. Factorial experiments allows us to study the interaction between factors on the response variable. We are going to deal much on the concept of interaction when it comes to factorial, because once you do a factorial experiment, you may not just look at each factors now in isolation. You may also want to consider the interaction between the treatments and how such interaction have an influence on the response variable. That is very, very important actually. We are going to deal much on that one. Now, I've decided to give a bit of a historical note of factorial experiments. Dear students, I want you to take note that this is not a theoretical course. Whatever we are studying has got started somewhere. We should not study this thing as if we cannot trace where it started. Most of the concepts that we are studying, you can also go back and say who started this, where and what was going on, and how did that evolve into what it is today. Factorial designs, likewise, were used in the 19th century by John Bennett and Joseph Henry Gilbert of the Rothamsted Experimental Station. Ladies and gentlemen, I've given you the link here. This link is not to cite the information which I've given above. I'm giving you this information because this is the current site that is used by for the Rothamsted Experimental Station, and you can see it's in the United Kingdom. Why I've decided to put this citation, I want you to take your time to go and study. There is one key important aspect regarding Rothamsted. This is where, say, Ronald Alma Fisher, I'm sure this is not a new term, a new name to you, Fisher, also worked. He worked there for quite a number of time, quite a great statistician. The current ANOVA, the analysis of variance that we talk about, is actually a brainchild of this guy, Fisher. The F test, when we say F is actually taken from his name Fisher. It's in honor of the proponent of the distribution. So, likewise, this is where also factorial designs started. That is why I have actually highlighted that one. Ronald Fisher argued in 1926 that complex designs such as factorial designs were more efficient than studying one factor at a time. I totally agree with the notion that, say, Ronald Fisher presented then. In fact, Fisher wrote, these are his words, no aphorism is more frequently repeated in connection with field trials than that we must ask nature few questions, or I deal one question at a time. The writer the boldness is mine. I'm the one who highlighted. The writer is convinced that this view is wholly mistaken. What is Fisher saying? Fisher is simply saying the aspect or the idea of investigating one factor in a single experiment and then we move on to the other and then we move on to the other is a complete mistake in biological experimentation. So, in short, this great statistician is advocating for factorial design. Instead of committing this blunder or this mistake, why not just combining factors and test them in a single factor? In a single experiment, pardon me. Now, in 1920, that is 1926, yes, when Fisher discovered this design, Frank Yates made significant contributions, particularly in the analysis. Now, you see there is an issue of the design, the layout in the field. Then comes the issue of how to analyze the data that is collected from that specific layout. So we can see Yates taking over. This is what we call research. One person discovers something, the other person takes over from what has been discovered and moves forward. And the other person also comes and takes over from the second person's end point and moves forward. So, say Ronald Fisher discovered the factorial design. Yates made some contributions, significant contributions in the analysis. Now, but since 1926, the term factorial was only used from 1935 when Fisher used it in his book, The Design of Experiments. I want you to go to the site, this site. There are a lot of materials. I'm sure you will gain a lot. Just read to understand so that you see we are not doing theory here. These are living issues. Today in the United Kingdom, a number of these publications which were made by these great statisticians, they still live up to today. They are still workers at Rothamsted. Research is continuing there. So I want you to just visit the site, try to check what is happening at that particular experimental station. I know in our country we have a number of experimental stations which are also equally mandated by the government to do research in various fields. So this is for the United Kingdom. We have ours in the country. So that is the setup. Now let's move on. I want us to look at the type of factorial. So what we have in this table, dear students, we have factor, level, design, number of treatments, replicates, number of experimental units. Don't try to memorize this. Here I'm just trying to illustrate that when we say it's a 2 by 2, 2 by 3, 2 by 2 by 2, 2 by 2 by 3, 4 by 3 by 2, 4 by 4 by 2, these are specific factorial designs which takes their name from the nature of the number of the factor and the nature of the levels within the factor. Now, let me start with the simplest one. If we've got two factors and the levels are the same, say for example 2 levels, then we have a 2 by 2 experiment. Let me perhaps try and give you a simple example for this one. If we are testing, say, spacing in an agronomic setup. So suppose we have S1, S2, Now these are different spacing dimensions. And suppose we are also interested in two types of fertilizer, F1, call it F1 and F2. So what it means here, spacing is a factor and fertilizer is a factor. So we have two factors. But these factors, spacing and fertilizer, they also have the same level. That is 2 for spacing and 2 for fertilizer. So in that case, we have a typical design called a 2x2 design, which is what is illustrated here. Now, the number of treatments per replicate, complete replicate, will be 4, because if you look here, we will have the combinations F1, F1, S1, and the F2, F2. I'm simply forming the combination S1, and then we will also have F1, S2, and we'll also have F2, S2. These are the four number of treatments that we are referring to. Right, if we decide to carry this experiment using 3 reps, for example, remember in an experiment, minimum replicates normally recommended is 3 for any meaningful results. You don't have 2 replicates. That is an extreme case. In most cases, you won't have any meaningful results from there. So 3 and above are recommended. Now, if we use 3 replicates, the number of experimental units, remember the experimental units is simply refers to those elements that are receiving the treatments. The elements that are receiving the treatments. It could be animals. Experimental units can be fish. If you are testing formulations, you mix some feeds and you want to give to the fish. So if you have got 4 treatments, obviously for a single replicate, you would also require 4 fish, because one will get this, the other one will get that. So, but if we have the 4 treatments, like in this case, and we replicate 3 times, the number of experimental units required will be 12. So likewise, I think if the factors are different, for example, 2 by 3, this becomes straightforward. We are just multiplying. And in the case of 3 replicates, we'll have 6 by 3, which is 18 experimental units. So you please analyze this table. The same applies here for a 3 factor. If they are the same, if they are different, and these are the combinations. And I want you, maybe let me emphasize, let me highlight here. You can see that if you've got 4 by 4, 3 factors, and each one of the factor has got 4 levels, the other one 4 levels, and the other one is 2 levels. Number of treatments for a single replicate is 32. I can assure you that for agronomic experiments, you cannot have a block of size 32 with 32 plots. This is what it means. And still expect that block to be homogeneous. So if you replicate 3 times, such experiment will require 96 experimental units. So in this case now, this type of factorial may not work. If you have got this type of factors, you may actually need to drop one of them. So either you drop the one with the 4, and then you do a 4 by 2, which then goes back to 2 factor, and then you do the other factor separately. They shouldn't be a compromise in terms of accuracy, in terms of quality. It's not just about time, reducing time, but it has also to do with the quality that you get thereafter. Now, Let's move forward. I've introduced the type of factorial experiments, which in most cases is also defined by the number of factors and the nature of the levels of those factors. Now, I want us to look at the type of effects in factorial experiments. Type of effects in factorial. Two factors are said to interact if the effect of one factor changes as the level of the other factor also changes. Let me go back here. If we talk of spacing and fertilizer, we are saying spacing interacts with fertilizer if, for instance, suppose at space, if we use spacing 1 with the fertilizer 1, if yield is say 30 tons per hectare for S1 under F1, if we use S1 under F2, suppose the yield goes to 45 tons per hectare, one would ask, what has caused the change from 30 tons per hectare under S1 F1 to 45 tons under S1 F2? Obviously, it can't be S1 because S1 is fixed. Instead, it is F. It is F because F has changed from F1 to F2. So that is basically what we are saying here. Two factors are said to interact if the effect of one factor changes as the level of the other factor changes. Now, consider a two-factor experiment, factor A and factor B, each with respective two levels, A0, A1, that is for factor A, and B0, B1, that is for factor B. So the four treatment combinations are, I'm sure you won't have problems in appreciating this. So these combinations will form a single replicate or a single block. In a single block, all these combinations will have to be put. Right? Now, let's move on. We want to define types of effects in factorial experiments. We define and describe the measurements of the simple effects and the main effects of each of the two factors A and B for us to compute the interaction effects. Ladies and gentlemen, dear friends, I want us to really take note of these terms that I've underlined. Simple effects, main effects, because that is very, very important for us to be able to understand the concept of interaction. This concept of interaction, of course, I've seen a number of videos on YouTube that talks of interaction. And I would encourage you to go on YouTube and type interaction of factors in an experiment. Please watch as many videos as you can. Try to appreciate the concept. Of course, I will explain here, and we are going to do some numerical examples in the next video. But I want you also to take the initiative to try and understand the concept of interaction on your own. Now, what is simple effects of factor A? What do we mean when we say simple effect of factor A? The simple effect of factor A is the difference between its two levels. At a given level of B. The difference between its two levels. What is happening? Simple effect of A at B0. You see? It will be A1 at B0 minus A0 at B0. You see, we are saying the simple effect at B0. So B0 is fixed. B0 is fixed. So the simple effect of A, we fix B0. And we want to see how does A change with its changes in the level, while B0 is fixed. So that gives us the simple effect of A at B0. So it will be the difference. If this is equal to this, the simple effect will be 0. But we are simply saying A1 at B0. Then we look at what happens at A0 at B0. That will give us only the simple effect of A. I wish I could be on a board. Of course, I will illustrate to you this in the next video where I will record using, and I'll be able to write a lot for you to see what I'm talking about. But I want you to appreciate the simple effect of A. Look at the definition. It is the difference between its two levels at a given level of B. We fix B0 because we are looking at simple effect of A at B0. B0 is fixed, and we check what will be A, what will happen to A at one of its level and at another level. We also define at B1 in a similar manner. We fix B1 and we check A1, the difference between A1 at B1 and A0 at B1. I hope, my dear friends, you can easily understand here. So we can also define the simple effect of B at A0 and also B at A1. I'm sure you must be able to appreciate this same explanation like what I've given. Simple effect of B at A0 and simple effect of B at A1. Why do we need these simple effects? This is how we end up getting the interaction. This is how we get the interaction. So at this point now, we are able to define the simple effect. Let us move on to look at the main effects. The difference between the simple effect of a factor at a certain level of another factor and then the main effects of factor A. It is simply the average of simple effects of factor A over all levels of factor B. The average, the average of two things. We add, we get the sum of those two things and we divide by 2. So we are saying the main effects of factor A, it is the average of simple effects of factor A over all levels of factor B. Look at this one, this part here. This is the simple effect of A at B0. Simple effect of A, factor A at B0. Simple effect of factor A at B1. Look at the definition of main effect. Is the average of simple effect of factor A over all levels of factor B. Remember, factor B has got two levels, B0 and B1. So the average, that's why we are dividing by 2. Dividing by 2 because we are looking at the average. So here, this is the effect, simple effect of A over B0, simple effect of A at B1. So the average of this gives us the main effect. So the main effect of A is simply average of this plus average of that one. I want you to check properly. Of course, you will practice this for you to appreciate what we are talking about. So we have defined simple effects and the main effects. Now look, the main effects of B is the average of simple effects of B over all levels of factor A. That is A0. You see, this is the effect of B over A0, and this is the effect of B over A1. So the average of this, if we add this, average of this plus average of that will give us the main effect of factor B. Think about it. These things are practical. Think about it. You will appreciate what do we mean when we talk of main effects. What do we mean when we talk of simple effects? Now, what is the interaction effect between A and B? This is very, very important. You see, we now define interaction effect between factor A and B as a function of the difference between the simple effects of A at the two levels of B, or the difference between the simple effects of B at the two levels of A. This is very, very important, ladies and gentlemen. A cross A by B simply means the interaction between A and B. And I want you to take note that it is the same as B by A. When we write like this, it's still the same thing. That is why even the definition here allows us to talk in terms of A towards B, and we can also talk of B towards A, and it is simply equal. So what are we saying here? We are saying it is a function of the difference. You see, the difference, this is the minus that we have, that is the difference. What is the difference between what and what? Simple effects of A at the two levels of B, you see. Simple effects of A at the two levels of B. Simple effects of A at the two levels of B. Simple effects of A at the two levels of B. So this is the simple effect of A at B1. Simple effect of A at B2. At B0, sorry. So the average, so here we can actually divide by 2, and we divide by 2 here, but here we've put the big bracket after factoring out 2 so that we just divide once. So that is the interaction. When we are saying calculate interaction, we are simply saying get the difference between the simple effects of A and the two levels of B, or the difference between the simple effects of B. This is now the simple effects of B at A1, and the simple effect and also effect of B at A0. The difference, the average of the difference, will give us the interaction. My dear friends, I have given you an example here. Numerical example to be done by students. Unfortunately, I'm not going to do this in this particular video. In the next video, I'm going to use the same data as the starting point towards introducing you how the analysis of variance for a non-replicated factorial and for a replicated factorial, where I will then use the board for easy illustration and for you to be able to follow clearly. So here I've given two examples. Consider the yield data in tons per hectare for two varieties V1 and V2, and two nitrogen levels, that is N0 and N1. Obviously, you can see that this is a factorial experiment where we've got a variety and we also have fertility. So variety is at two levels, V1 and V2, we've got two varieties, and the fertility, we've got two nitrogen levels, N0 and N1. So the data that I've given you is hypothetical. It's not real data, but it is given in such a way that you will be able to appreciate the concept of interaction and no interaction. So I have given you the data where there is the interaction present, and also I've given you the data where there is no interaction. Dear friends, what I want you to do, using this video, I want you to calculate the simple effect, the main effect, and the interaction under interaction present, under no interaction, and also produce a graph. And I want you to see what the graph will look for, the interaction graph. How will the interaction graph be compared, this one versus this one? The graph double ticks versus hash. Is that hash? Yes. So, using each of the data in the formulas given, calculate all the simple effects, all the main effects, interaction effect using the no interaction data, produce an interaction graph, and do the same for the interaction data. How does the interaction and the non-interaction graphs look like? Any challenges in this work, consult your teacher. Dear good students, I think this is the end of this video. This is an introductory video to factorial experiments. The next video will sum up everything. I will demonstrate the calculations, of course starting with this example, which I want you to do before you see the answer from me, so that you see the whole idea. Just use the formulas here. What is your A naught? What is your B1? What is your B naught? Plug in the formula, you can get the interaction, you can get the main effects, you can get the simple effects. But the only difference now is that you are actually using the data. Which one is your A naught? Which one is your A1? You can choose any A naught, A1. You see? Then you plug into the formula. There is nothing new, really, nothing difficult. So what we've covered here, I've given you what a factorial experiment is, the motivation behind factorial design, given you the different types of factorial experiments, and I've also given you the historical notes, that is the origin of factorial design, which we've traced back from 1926, propounded by, say, Ronald Fisher, and also some additions done by Yates. And then we moved on to look at the effects in factorial experiment. That is the simple effects, the main effects, which are so critical effects in enabling us to calculate the interaction effect. So the simple effects and the main effects are needed for us to calculate the interaction effect. Because when we do a factorial experiment, we said basically we would then need to get the interaction. We are going to start here next time, where we are going to give details of interaction. Actually, we are going to start with this example, and then we conclude the factorial experiment by looking at a couple of examples, numerical examples, where we need to establish how to get the different sum of squares and so forth, and complete an analysis of variance for factorial experiments. Thank you very much. Enjoy. Go through several times. Try to appreciate the concepts. I thank you.